In this lecture, I'm going to cover chapter 2 of the textbook, which is available online here. You can get the source code for the book at this link, and if you want a physical copy of the textbook, you can get it from here. So I'm assuming that you will at some point read chapter 2 as well, apart from watching this lecture. But let's walk through the basic storyline in this chapter. So in chapter 1, we introduced the idea of conditional probability, and we derived Bayes' rule in that chapter. So I didn't discuss that in the chapter 1's lecture, video lecture, but it's a pretty straightforward derivation which I will just show you. So the conditional probability rule is something like this. The probability of, let me write it here, the probability of some discrete event A given that some other discrete event B has happened is the joint probability of A and B happening, right, divided by the probability of B happening, assuming of course that the probability of B is greater than 0, because dividing by 0 is not really a defined operation. So this is the conditional probability rule that we saw in chapter 1. And so one interesting thing to notice in this rule is that the probability of A and B happening is the same as the probability of B and A happening, right? So if that's the case, then I could just flip these symbols A and B and write another version of this equation, which would be something like probability of B given A happening is equal to the probability of B and A happening divided by the probability of A, right? So now, as I mentioned, because of this equality, right, we have this term. Wow, these colors are not working nicely. So we have this term here, and we have this term here, which are oh, sorry, I didn't mean to write that, so let me try again. Not this one, just ignore this. I'm talking about these two terms here. They are basically identical, right? So because they're the same probability, the same joint probability, I can now equate the probability of A given B times the probability of B with the probability of B given A times the probability of A. So what I've done here is that I've taken this equation and expressed it in terms of the joint probability of A and B. So I've just multiplied both sides with the probability of B. So on the left hand side, I would get the probability of A given B times the probability of B. That's this here. And then similarly in the second equation here, right, what I'm doing is I'm just expressing the joint probability of B and A happening as the product of probability of B given A times the probability of A. That's this term here. And these two are going to be equal because the probability of A and B happening is the same as the probability of B and A. And this is what gives us Bayes' rule. So Bayes' rule is not anything controversial or subject to dispute. It's just a consequence of the conditional probability rule. Okay. So what this gives me, this last line, what it gives me is that what I get out of this is that I can express the probability of A given B in terms of all the other other terms in this equation. So I could simply write the probability of A given B is, so I'm now dividing both sides by the probability of B, right? That would be the probability of B given A times the probability of A divided by the probability of B, right? So So this is what gives me Bayes' rule. And that's what you're seeing over here in this equation here. That's how this rule is derived for discrete events. Okay? So having done that, what we are going to do now is we're going to think about this Bayes rule in the context of probability density functions. In this part of the lecture for chapter 2, I'm going to walk you through an analytical example of the application of Bayes' rule for data analysis. This is the beta binomial conjugate case, and the story works like this. So suppose we ask subjects to complete a sentence, right? We show them an incomplete sentence, we ask them to complete it with one word, and we stipulate that the correct word that we are expecting them to put in is the word umbrella. So let's say we have 100 subjects, each of them sees one instance of this sentence, just one sentence. And let's just assume as a thought experiment that 80 of those 100 subjects produce the word umbrella as the continuation and 20 produce some other word. So in that situation, the maximum likelihood estimate of the theta parameter in the binomial distribution, which would be the assumed distribution that's producing such data, because you have correct and incorrect responses, so 0, 1 responses. So the MLE, the maximum likelihood estimate of theta, would be 0.8. We discussed that in chapter 1, right? So one interesting thing to notice here is that the variability of this estimate, as I also discussed in chapter 1, the variability of this estimate is going to depend on the sample size, right? So suppose I do 100 experiments, each of sample size 10, okay? And I compute the standard deviation of the estimated means, right, under repeated sampling. So that means I've done 100 experiments and I've got 10 subjects each time, and so each subject is giving me one data point, a 0 or a 1, okay? And so let's say the true probability of producing a correct response is actually 0.8, right? This is just a thought experiment. Under repeated sampling, for 100 experiments, the standard deviation of the maximum likelihood estimates that we would get in each of those 100 samples is this number here. But now if I increase the number of trials to 100, what you'll notice is that under repeated sampling, the standard deviation of the estimate of theta will become much narrower, right? So the variability in the estimate of theta will change as a function of the sample size that I have, right? So this is a very important detail in frequentist statistics, because when we compute a maximum likelihood estimate, we are interested in the frequentist world. We are interested not only in the maximum likelihood estimate, but also the uncertainty of our estimate of the variability in the estimate, right? So that's the standard error that we are interested in, right? Because if the standard error is very large, I'm still talking like a frequentist right now. If the standard error is very large and we've got a maximum likelihood estimate with a very large standard error, what that is telling us is that under repeated sampling, hypothetical repeated sampling, we would get different, very different numbers for the estimate, right? So there would be a lot of variability. If the standard error is very small, right, then we would have very little variability in the theta estimate. That's the significance of this variability as a function of sample size in the frequentist world, right? So, in the frequentist paradigm, the theta parameter in this example is assumed to be an unknown point value out there in nature, and we are trying to estimate that value from the data, right? But it's really a point value, it's not a random variable. It's just a point value unknown out there in nature, and we are trying to estimate it. And the whole frequentist way of thinking crucially depends on the properties of this estimate under hypothetical repeated sampling. Now in the Bayesian approach, we are going to take a radical step away from this way of thinking. Instead of thinking of the theta parameter as a point value that's unknown and out there, we are going to treat the theta parameter as a random variable and associate with that random variable a particular probability density or mass function, right? So let's just say, for example, that we could start with the assumption that the theta parameter, the probability parameter, is a random variable with a uniform distribution defined on it. So a uniform distribution goes from 0 to 1, that's the support of the distribution, and every value between 0 and 1 is equally likely. So it looks like a rectangle. Okay? So what that distribution would express as a belief is that all possible values of theta are equally likely, right? So that would be one example of a prior distribution on the theta parameter. And this is a radical shift away from the frequentist way of thinking, because now we are assigning a prior distribution to the theta parameter. And this will now play a role in our Bayes rule computations, as you will see. Okay, so now once we do this kind of, make this kind of step where we assume a prior on theta, so what will happen is now that if I just generate a bunch of random data from a uniform distribution ranging from 0 to 1, let's say I've generated 100 data points from a uniform distribution that represents, plausible values of theta, a priori plausible values of theta, and I repeatedly compute the estimated means and the standard deviations of those estimated means under repeated sampling. What's going to happen now is, because what I'm plugging into this equation is no longer a point value. Remember what I did earlier? I plugged in a point value. That was my assumed true value for theta. Instead of assuming a true value for theta, I'm assuming a prior distribution for theta, and I'm taking some samples from the uniform distribution and plugging those in. So I'm plugging in 100 different values here for theta under repeated sampling. So what that does is that it increases the uncertainty of the estimate of the theta parameter. And that additional uncertainty, if you compare this number, right, so with 100 experiments, each of trial 10, I did that earlier, what you see is a standard deviation of the estimated theta parameters is 0.12, but now because I've added a prior distribution on theta, theta is no longer a point value, now the standard deviation is 0.33. Okay, so the uncertainty about the estimate of theta has increased as a function of the prior distribution that I specified on theta. Okay, so really what I'm trying to show you here is that by making this move away from the frequentist way of thinking, by treating the theta parameter as a random variable, in other words, assigning a prior distribution to the theta parameter, we are now introducing a source of uncertainty in our estimate of the theta parameter. Okay, so I'm going to make this idea much more concrete in the coming minutes. So, another example of the effect of variability in the prior distribution for theta on the standard deviation can be illustrated by changing the prior distribution for theta such that it has a much narrower range. Instead of ranging from 0 to 1, right? Suppose I narrow the prior distribution on theta to range only from 0.3 to 0.8, but still a uniform distribution. The uncertainty has gone down, right? The prior uncertainty of theta has gone down. And so if I rerun my simulation with variable values for theta in here, right? What I will get is a standard deviation that's not quite as high as the one that I got when I assumed a uniform prior between 0 and 1, but it's still higher than when I assumed a point value, true point value for theta. All right, so basically the point I'm trying to get across here is that the prior that we define on the parameter here, theta in this case, is going to affect the uncertainty of the parameter estimate that we're going to get once we've seen the data, right? So let's try to carry out a Bayesian analysis for this particular situation where we are assuming a binomial likelihood for the data, right? The situation is we have 100 data points and we have 80 successes out of 100. So that's the binomial distribution that we saw in chapter 1. So we're going to assume the probability mass function shown here where I have n equal to 100, k equal to 80, and theta is now a parameter that will have some prior distribution associated with it. It doesn't have a fixed value. We don't know what the value is. Of course, the frequentists don't know this either. They estimate it from the data with the maximum likelihood estimate. But what we are doing is that we are taking an additional step and defining a prior distribution on theta now. And we're going to use Bayes' rule to work out the posterior distribution of theta given the prior and this likelihood function here. All right, so here's my likelihood function, right? So you notice that I've plugged in all the values that I know. The data have been collected. I know the numbers, 180, not 180, but 180. And the only variable now is theta, so that's the likelihood function now, right? So we could have written it like this, and normally I will write the likelihood function in this way, writing k and treating theta as, you know, in the conditional part of the distribution. So k is the number of successes conditional on n equal to 100 followed by theta. I'm still treating this as a likelihood function, even though technically I would want to write the likelihood function like this because that's how I used it in chapter 1. So don't be confused by the fact that sometimes theta ends up, you know, to the right of the vertical bar and sometimes to the left of the vertical bar, right? So what I'm doing is I'm simply fixing constant values here, and the value that is not fixed, that is the variable here of interest, right? So we can write the likelihood function like this, and from now on we will be writing it in this manner. So please don't be confused about that. Okay, so you know, we have the likelihood function. Remember Bayes' rule? If you go back to Bayes' rule, right? So what we have is we've defined this likelihood function, right? We have this laid out. We just need to work out a prior in order to carry out this computation, right? So we're going to do that next. So let's think about what a plausible prior for theta should be. Theta is a probability, so theta has to have a prior that ranges from 0 to 1. The uniform prior was one such prior distribution that we could have chosen, but there is another distribution that is really appropriate for this particular situation, and that's the beta distribution. So what you're looking at here is the probability density function for the beta distribution. The beta distribution is defined in terms of two parameters, A and B. And the way you can think about these parameters is that A can be seen as your prior belief about the number of successes you would expect, and B as your prior belief about the number of failures that you can expect, right? So if I assume a priori that I have a 50-50 chance of success and failure, then I would set A and B to be the same numbers, right? So for example, A equal to 4 and B equal to 4 would represent a belief about belief that we have a priori. We believe that in 8 trials I would get 4 successes and 4 failures. If I set A and B to 20 each, then the belief that I'm expressing is that in 40 trials I have 20 successes and 20 failures. So these two parameters will control the shape of the distribution of the beta distribution, as I will just show you. So the beta distribution is this term here, and this part here in the beta distribution is the normalizing constant that I mentioned in chapter 1. This is the kernel of the distribution, and so this kernel will play the crucial role of determining the shape of the distribution. The BAB section that you're seeing here, this is just the integral of the kernel, as I discussed in chapter 1, that makes sure that the area under the curve for this parameter sums up to 1. Okay, normalizing constant. All right, so here are some illustrations of what you can get for different parameterizations of the beta distribution, right? You could have, if you set beta to 1 and 1, if you set the A and B parameters to 1, then you will end up with a uniform distribution. If you increase the values of A and B but keep them equal, for example, A equal to 4, B equal to 4, that's this one here, over here, you will see a symmetric distribution that has a lot of variability in it. So if I define a prior distribution, a beta distribution with A equal to 4 and B equal to 4, what I'm saying is that I believe that the theta parameter has a mean of 0.5, but I'm pretty uncertain about the variability of that, a priori variability of that theta parameter. So the theta parameter could be as large as, this number here, or as small as this number here. Now, taking the other extreme, right? If I were to increase the A and B parameters to 10, you'll notice that the uncertainty of the distribution, of the beta distribution, goes down, right? So the beta distribution gets tighter around 0.5. So the greater the values of A and B, keeping them equal, the tighter the distribution will get. So the A and B parameters basically serve the purpose of allowing you to express mathematically your prior uncertainty about the theta parameter. Now this prior uncertainty, where does it come from, right? It could come from your prior knowledge about the theta parameter from previous experiments. It could come from expert knowledge about the problem that you're studying. It could come from just a rough guess that you have of plausible values of that parameter, right? So I'm going to unpack that in great detail, how you decide on the prior distribution much later, but right now we just need to understand what the A and B parameters do to modulate the shape of the beta distribution and what they tell us about, what they express about our beliefs about the theta parameter before we have seen the data, right? So all this, the decision about which prior to use is made before seeing the data, right? It's the prior distribution. That's why it's called the prior distribution. Right, and so these are symmetric distributions I showed you, but they could be non-symmetric as well, right? So you could have, if you had 10 for A and 1 for B, so this would skew the distribution towards the right. You could skew it towards the left by flipping the numbers here. So you can see different possible variations on the beta distribution here. There's one more possibility that I forgot to put here, or maybe I didn't want to discuss it here, but I'll do it anyways. If you set A equal to half and B equal to half, you will get this U-shaped distribution with higher density on near 0 and 1 and a kind of valley, in between. So, but that's not a distribution that I have ever used for modeling, the prior distribution of theta in any realistic setting, but in principle it's possible to have that. Right, so the beta distribution has defined for it the expectation and variance. So these are all analytical results that one can derive, and the expectation and variance is in terms of the A and B parameters, right? So you can see intuitively that this expectation makes a lot of sense because it's the number of successes divided by the number of trials, which is the maximum likelihood estimate for the theta parameter in the binomial distribution. One interesting thing I want to introduce here is the application of the Q beta function. So remember the dpqr family of functions? They play a very important role in helping us understand the properties of the prior distribution. Of course, we can understand the properties of the prior distribution we decide on for theta by graphically summarizing them. And in fact, it's a very good idea to always graphically summarize them, to eyeball the distribution to see if it's a plausible distribution that you can use as a prior. But one can quantify that by just computing the 95% credible interval for a particular prior distribution that you might be interested in using. to understand what the range of plausible values are that you're assuming for that parameter. So suppose I assume A and B to be 4 in the beta distribution. In R, A is written as is called shape 1 in the beta family of functions, and B is called shape 2. Don't ask me why. Okay, so we have A and B as shape 1 and shape 2, and what we can do with the Q beta function is find out the quantiles such that 95% of the area under the curve in the beta 4-4 distribution is covered. Okay, so and the quantiles then are these two numbers here. So what these two numbers represent is a belief that theta lies between these two numbers with 95% probability. That's my prior belief that I'm expressing by setting A and B to 4 in this prior distribution. Okay, so that's how we reason about plausible priors for a particular problem that we are working on. If I were to now say, okay, this prior is too wide given my beliefs about the particular problem I'm working on, I might have prior knowledge about the problem I'm researching, right? So if I want a narrower prior, I could increase the A and B values to 10. So you can see that with a higher A and B parameter, the credible interval becomes tighter. So if I kept increasing A and B, let's say I change it to 100 and 100 for A and B, I would get an even tighter credible interval, right? So that's how you can think about the prior distribution graphically and by using the Q beta function. Okay, so now because the beta distribution is defined, the kernel of the beta distribution is defined as theta A minus 1 and times 1 minus theta B minus 1 if I were to choose A equal to 4 and B equal to 4. So that's this prior here, right? This prior here with this 95% credible range for the prior distribution of theta. Then the prior distribution that I'm assuming for theta is this term here. Okay? That's what I've got as my prior distribution. So let's now use this prior alongside the likelihood, the binomial likelihood that we have for the data. Okay, let's take a look at how this will work. So that's what I'm going to talk about next. So we are now going to just apply Bayes' rule to multiply the likelihood and prior. Okay? And of course I'll talk about the marginal likelihood in 1 minute. So let's replace in this equation, this is of course written in English, but I'm just going to translate it into the mathematical forms in a moment. So we're going to first write the likelihood in terms of the data that we have, right? So we've got the theta parameter and we've got n and k specified because we already collected the data. We have 80 successes in our thought experiment out of 100 trials, right? So my likelihood function is going to be this expression here, right? So you got 100 choose 80. Theta to the power of 80 times 1 minus theta to the power of 20, right? So this term here is my likelihood function. And this term here, the second term here, is my prior, which I just specified a few minutes ago. So that's my beta 4-4 prior, right? Now, in the denominator, I have the marginal likelihood with k equal to 80 being the observed data that I have, right? So what the denominator would be doing is, as I mentioned earlier, it's the normalizing constant. And because it's going to be a constant, we can actually ignore. So if you just think about the numerator now, right? In the numerator, I've got the kernel of the likelihood function, theta to the power of 80 here, 1 minus theta to the power of 20. I'll just talk about the square bracket stuff in a moment, okay? So here's my likelihood function. And here's my kernel of the prior. Okay, so here's the kernel of the prior distribution for theta. Right, so this is the interesting part that I want to focus on for the moment. This is the numerator in the Bayes rule computation. Right. Now, moving back to this square bracket here, the square bracket that I pushed aside to the left is really all the constants that are in this equation, right? So if you think about it, the only variables in this equation now are the terms that involve theta. Anything that doesn't involve theta is not a variable, it's a constant term. So I moved them here, so A 100 choose 80, the B44 term, and the denominator pk equal to 80. These are all constants here on the left hand side, okay? And in fact, what this square bracket term represents is the normalizing constant, right? And because it's a constant, we can just put it aside for the moment and just focus on the two kernels of this distribution. Now, if you look at these two terms here, right, the likelihood and the prior, you'll notice something very interesting. The interesting thing is that I have a theta term here, I've got theta here, and I've got theta here, and I've got 1 minus theta here and 1 minus theta here. And what that means is that now I can simply multiply this straight away and get a new expression. So let me just try doing that, okay? So I've got theta to the power of 80, and that's this term here, and I'm going to take this guy here and put it alongside that theta, so that theta to the power of 3, and now I concentrate my mind on 1 minus theta, that is to the power of 20, right? And I'm going to multiply that. I'm going to take out this term here as well, 1 minus theta, which is to the power of 3, right? That comes from the prior. So now if you look at this equation here, this is easy to simplify because I've got the same variable theta here, the same variable 1 minus theta here, and some exponents here. So I'm just going to add up the exponents, right? So it would be 30 theta 83 and 1 minus theta 23, right? So what this gives me now is the kernel of another distribution. And what is that distribution? It's the kernel of another beta distribution, right? Because remember, the beta distribution, the kernel of the beta distribution looked like this. It was theta sum A minus 1 and 1 minus theta sum B, sorry, minus 1, right? That's what the kernel of the beta distribution was. So this term here represents the term A minus 1, and this term here represents the term B minus 1. Now A and B were the priors that we had defined, earlier for the theta distribution. So I'm going to call this A star and B star to distinguish them from the priors, because what this means now is that A star minus 1 is equal to 83 and B star minus 1 is equal to 23, right? And what that means is that A star and B star, these are the new parameters, the updated parameter, hyperparameters we call them, right? These are the updated parameters of the beta distribution after I've seen the data, right? So what does that mean? What is A star going to be? It's going to be 84, and what is B star going to be? It's going to be 24, right? So 84 and 24 are the new A and B parameters that represent the posterior distribution of theta after I've seen the data. So what I just did is I did an analytical example that gives me the posterior distribution of the theta parameter after I've seen the data. That's all there is to it. Like, it's very, very straightforward here. The only thing that's missing in this calculation is that I don't have the normalizing constant. But as I mentioned in chapter 1, that normalizing constant is easy to compute now. Okay? So what we got as a result of the Bayesian analysis that we did was we got a new A parameter which is 84, and a new B parameter, which is 24, after we saw the data, right? So this is the posterior distribution of the theta parameter. However, this posterior distribution, this is just the kernel of the posterior, right? And of course, the area under the curve for this distribution is not going to sum up to 1. So let's just compute what the area under the curve would be. So I just did this just like I did in chapter 1. I just took the updated parameters a and b, defined a function using the kernel of the distribution, right? Just the kernel here, right? And I computed the area under the curve ranging from 0 to 1, which is the support of the beta distribution. So the beta distribution ranges from 0 to 1. That's why I've specified these limits here, right? So I get the area under the curve here. And so basically what I'm doing here, this integration that I'm doing here is literally calculating this integral from 0 to 1, right? And that's the normalizing constant, because if you think about this equation from chapter 1, there is some normalizing constant for this equation, and I can compute that normalizing constant by just dividing both sides by this integral, which is what I've done here. So 1 over the area under the curve that I just computed, this I just computed here, gives me the normalizing constant, right? And so if I were to now compute, here's my kernel of the posterior, right? This term here is the area under the curve. This term here is the area under the curve I just computed. So what I'm doing now is I'm now defining a new function that contains a normalizing constant. And if I compute the area under the curve now, I get an area equal to 1, right? So the main point I'm trying to get across here is that we do the calculation focusing only on the likelihood and the prior. So this term that I got was a result of multiplying the likelihood, the kernel of the likelihood, with the kernel of the prior. Once I have that, in this particular example, it is straightforward for me to figure out the normalizing constant. So I'm going to ignore the normalizing constant and only compute the posterior distribution of theta. What we say is that we're going to compute the posterior distribution of theta up to proportionality, right? If you go back here, if you look at this equation here, this is just the Bayes rule again, but the denominator is gone. That normalizing constant I've ignored, and instead of an equality sign, I've got a proportional to sign here. And so what we are saying here is that we are computing the posterior up to proportionality by multiplying the kernels of the likelihood and the prior. Okay, so that's what I did. And once I have the kernel of the posterior, I can work out the normalizing constant straightforwardly. So to summarize, what we did so far in the beta binomial case, right? We decided on a binomial likelihood for the particular problem that we were working with, 0-1 responses. And we defined a prior on the theta parameter, a beta 4 prior. We multiplied the likelihood function, more precisely the kernel of the likelihood function, with the kernel of the prior probability density function. And we obtained the kernel of the posterior distribution up to proportionality, and that gives us the posterior distribution of the theta parameter. So as you noticed, the posterior distribution of the theta parameter has the same probability density function. The underlying form of the probability density function is the beta distribution. Why? Because once I did those multiplications, these multiplications that I did, that gave me this term here. This kernel is exactly the kernel of the beta distribution, right? So what happened is I started with a binomial likelihood, I multiplied with a beta prior, and I got back a posterior distribution that's also a beta, right? So that's why this particular example is called the beta binomial conjugate case. A conjugacy here means that what you have as the prior, the form of the prior is going to remain invariant when you get to the posterior. If you have a beta prior, the posterior will also be a beta prior, of course, with updated parameters, right? So the shape of the distribution defined on the theta parameter does not change. Not the shape, I mean the underlying form, the mathematical form of the probability density function does not change. All that changes is the parameters in the beta distribution as a function of the data that you have seen, right? So that's called a conjugate case here, and there are many other examples of conjugacy in statistics. So for example, another famous example is the Poisson gamma case, which I will just discuss. Another example is the normal case, right? You have a normal likelihood and a normal prior on the mu parameter. The posterior on mu will also be normal, and so on. So there's several other cases like this. Okay, so now we know the procedure. The procedure is pretty straightforward, right? We start with the likelihood and prior, multiply the kernels out, get the posterior up to proportionality, and from there we can describe the posterior distribution because it is a familiar distribution that is identical in mathematical form to the prior distribution with updated parameters, of course. All right. So this example, the importance of this beta binomial example is not that you can use it in day-to-day life. In day-to-day data analysis, we are going to be working with much more complex data. We can't just use this simple beta binomial case in most of the types of experiments that at least that I do, okay? But the value of this simple beta binomial demonstration is to understand how the Bayes rule plays out in giving you the posterior distribution. The insight that you should take away from this example is to understand the interplay of the prior and the likelihood in determining what the posterior is. And I will, of course, unpack this in more detail in the coming part of this lecture. All right. So I've already explained that what a conjugate analysis is, right? So that's an example that we just looked at. So you can look at the formal definition of conjugacy later on and look at all the details there. But what's interesting in this particular beta binomial case is that we can actually derive a general solution for a beta binomial conjugate analysis, right? So the general solution is the following. No matter what n and k are, and no matter what a and b are in your prior distribution, right? So the a and b are the priors, the parameters that you define in the prior distribution for theta. You can write this, the product of the kernels of the likelihood and the kernel of the prior in abstract form using the variables n and k and a and b. Okay, so that's what I've done here. And so what I have is, this is the likelihood part, the kernel of the likelihood. This is the kernel of the prior, regardless of what a and b are and what n and k are. What will happen is that if you multiply out the thetas and the 1 minus thetas, you will get an updated set of a and b parameters in the posterior distribution of theta, such that the new a for the posterior distribution of theta will be a plus k. Remember, a is the prior, that the parameter we defined for the prior for theta. K is the number of successes, so a plus k will be the new a parameter. That's what I was calling the a star parameter, right, when I was writing out the analysis. And similarly, when we multiply out the 1 minus theta terms, what we will end up with is, let me just make this a bit bigger. Sorry. Right, so here's b plus n minus k, right? So remember, b was the parameter that we defined on the was one of the parameters that we used to define the prior on theta. N is the number of successes and k is the number of failures. So b plus n minus k is the updated b parameter, what I was calling the b star parameter, right? So what this means is that I can literally write out now a general solution for the beta binomial case. So if I'm assuming a binomial likelihood and a beta prior, I already know without doing any more math again, right? I can literally write down the posterior as what was it? A plus K and B plus N minus K, right? So these are my new A and B parameters. So this is what I was calling A star and B star to distinguish it from A and B, right? So these are my updated parameters. So this is the posterior of theta. And so formally I could write it like this. I could say that my new theta is coming from a beta distribution with these updated parameters. So if you are ever in a situation where you have to analyze independent data, let's say where you have n trials and k successes, and you need to figure out an estimate for the theta parameter in the binomial distribution, right? You can simply use this closed form solution. It literally takes 1 second, to do this computation to get the posterior of theta under different assumed A and B parameters for the prior distribution of theta. Now we come to the second analytical example, the Poisson gamma case. This is another conjugate case that is very instructive because it is very similar on the one hand to the beta binomial in the sense that we have a likelihood, a Poisson likelihood, and a gamma prior on the parameter in the Poisson likelihood. But at the same time, it has the illusion of complexity. So if you look at the equations that will come up in a few minutes, they will seem a lot more complex, but actually the machinery is exactly the same as in the beta binomial. So I will unpack the story for you, and you will see that regardless of the fact that the likelihood and the prior distributions that we are going to use in this example are somewhat more complicated, at least superficially. Underlyingly, the mathematics that we have to do is just the same as in the beta binomial case. So it's not as complex as it seems. And this example is very instructive because it allows you to understand more deeply how the likelihood multiplied with the prior ends up giving you a posterior that has the same form as the prior distribution on the parameter. So the concrete example we're going to start with is from a data set that we collected many years ago and published in this 2011 paper. So the data which will be available to you are total regression counts. Okay, so we are going to be looking at some eye tracking data, and what we are looking at is the total number of leftward eye movements at per word, right? The total number of leftward eye movements per word in some eye tracking study that was done. So the actual details don't matter at all. The scientific details don't matter. What matters is the structure of the data, right? So I have one subject's data here, and there are some conditions that that subject is being exposed to. There are multiple items that that subject is seeing, and these are the total regression counts. This is the variable column. It labels the type of data that we're looking at, and because of the width of this, the width of this screen, you're not actually seeing the values. So here are the values that show the total counts of regressions at each word in the sentence. So the word ID is not provided here, but the item ID tells you that we are looking at a particular word in a particular item, and here are the number of regressions from that particular word in that item read by this particular subject in this condition, right? So that's what these data look like. Here is 4 regressions, there's 0 in these 2, and so on. Okay, so that's the data. And now because these data are discrete, right? So you can have 0 regressions, 1, 2, 3, and 4. You cannot have 1.5 regressions, right? at a particular word. So this is discrete data, and we can summarize the data that we have in this data frame. So we have 0 as the minimum value, and the maximum value is 21. That's a large number of regressions. And there's a certain distribution. You can see that the median is about 1. So it's very rare to have 21 regressions from a word. Probably those regressions are happening at the end of a sentence. That can happen in some very rare cases. But more, you can see that even the third quartile has 2 here. So the vast proportion of regressions are few in number, and there's a few rare regressions, which could actually be just artifacts or something. But all that is beside the point. What's important is that what we are going to now do is we're going to try to think about a likelihood function that could have produced that kind of data. This kind of discrete 0, 1, 2, 3, 4 type of data points. What would be an appropriate likelihood function? It can't be the normal distribution. So you can't use a normal likelihood function here. What you could use as an appropriate distribution is the Poisson distribution. It's a discrete distribution. Here is the PDF associated with the Poisson, right? So for any data x, the Poisson distribution takes as input a parameter called lambda, and this is the shape of the distribution. The denominator here is the normalizing constant again. This is the kernel of the distribution, and this x exclamation mark is x factorial. So that means x times x minus 1 times x minus 2 all the way down to 1. Okay, so that's the x factorial notation that you will see again and again in this section of the recording, or this section of the lecture, I mean. So this lambda parameter in the Poisson distribution is called the rate parameter, and it will have to have a value greater than 0, greater than or equal to 0, and the x, the data, the support of the random variable that's assumed to be producing the data also has 0 as a lower bound. So the values can be 0, 1, 2, 3, 4 all the way to infinity. That's the support of x in this particular situation. Now, one thing I want to point out here is that in the discussion that I'm going to do right now, I'm going to assume that these data are all independent and they are coming from the same Poisson distribution. That assumption is false because I have repeated measurements here, so the data are not independent. I have multiple measurements from each subject, multiple measurements from different items. That's a problem I will deal with later on in chapter 5. But right now we're just going to pretend that the data are coming from, the data are independent, right? All the n data points that we have are independent. So in order to avoid getting hung up on the fact that the data are not independent, I'm going to just simulate some data here, 10 data points coming from a Poisson distribution. Here, notice that I'm using the R Poisson distribution again. Right, so this is the DPQR family of functions. Now I'm applying it in the Poisson case. So I'm generating n data points and I'm producing data from a Poisson distribution with an assumed lambda of 3. So that's the rate parameter. And so what you're going to see is a bunch of discrete numbers being pumped out of this distribution, and these values will be close to 3, right? So they will fluctuate around 3. They can be larger or smaller, of course, right? So these are random numbers that are being produced by the R-Poisson distribution. We can visualize this for the lambda equal to 3 parameter, right? So you can see the distribution of 10 generated data points here. 0, as I said, is the lower bound, and it has a skew to the right. But these are all discrete values here. Okay? There's nothing between 6 and 7, for example, right? Okay, so now, because we have a Poisson distribution with a lambda parameter in it, that's the rate parameter in the Poisson distribution, we are going to have to define a prior on the lambda parameter. Now, just as an example, let's assume that we know something about this lambda parameter from previous work, right? So suppose we know from previous research on eye tracking that the average number of regressions is 3. So the lambda is 3 based on previous research, and the variance that we observed in previous work is 1.5. I just made up these numbers. There's nothing special about these numbers. They may or may not reflect anything true about eye tracking. I'm just using them as an example. So now we know two things about the lambda parameter, which will help us decide on the priors for the lambda, the mean and the variance. So one interesting thing, about the lambda parameter is that we can actually assume that the lambda parameter is coming from a particular probability density function that is bounded at 0. That distribution, a very convenient distribution that we can assume as producing the lambda, is the gamma PDF, the gamma random variable, right? So the PDF for the gamma distribution for any gamma distributed data x would be described as follows. The gamma distribution takes two parameters, A and B, and you see on the right hand side here, for all values greater than 0, greater than or equal to 0, the PDF is this term here, and for any other value below 0, it will be 0. So the support of the PDF for the gamma is positive, which is what we want, because lambda can have 0 as a lower bound and can only have positive values. So the gamma distribution, the PDF for the gamma, is an appropriate distribution that we can use for defining a prior on the lambda parameter. So as I said, we know two things about the lambda parameter from previous work. In this hypothetical example, we know that the mean is 3 and the variance is 4. Now, if we assume a gamma prior for the lambda parameter, what we can do is we can actually figure out the parameters A and B, these parameters A and B in the gamma distribution, that would represent our prior belief for lambda. And we would do that by using the information that we have, which is that the mean of lambda from prior research is 3 and the variance of lambda is 1.5. We know that from prior research. Okay, so let's take a look at how this would work. Okay, first I want to show you how to visualize the gamma distribution, and then I'm going to show you how I'm going to derive the A and B hyperparameters that will determine the prior distribution on the lambda parameter that goes into this Poisson distribution. So remember, this is my likelihood. The goal I'm trying to achieve here is to figure out a prior for lambda. What I know is the mean and the variance of lambda from previous work, and I'm assuming a gamma prior on lambda, and I will explain in a moment why that gamma prior was chosen. I could have chosen something else, by the way, right? Later on, you can decide on other distributions, of course. But right now, for illustration, I'm using a gamma prior. The gamma prior takes A and B parameters. I'm going to figure out those A and B parameters, which are called hyperparameters, in order to do my Bayesian analysis. Okay, so that's where we are going. So before we do that, I want to just show you how you would graphically summarize the gamma distribution. In R, the gamma distribution is represented in terms, instead of writing A and B, and don't ask me why that is, instead of writing A and B as the parameters in the gamma, we have shape and rate. Okay, so in the R function, R gamma, which will produce random data from a gamma distribution, I can use shape, that means A, the A hyperparameter is here set to 3, and the B parameter, the rate parameter, is set to 1. So if I set the A and B parameters here, I can produce 10 random data points, which would look like this. This is a continuous distribution. It's not a discrete distribution. Okay. So that's why I've got a continuous line here to represent the gamma distribution here. Okay. So this is how I would visualize the gamma distribution. The reason I'm showing you how to visualize the gamma distribution is that when you're trying to figure out a prior for a particular parameter, it is a very useful thing to do to just plot your prior distribution, your assumed prior distribution, to get a graphical summary of what you think what it represents. right? So because the prior distribution represents your prior knowledge or prior belief about the parameter, and graphically you can view what you think is a reasonable range. So for example, in this example here, when I have a equal to 3 and b equal to 1, if this were the prior distribution for the lambda parameter, so gamma 3, 1, then I would be assuming that the rate ranges, is not larger than 8. Okay, it ranges from maybe 1 to 8 or something like that. Right? So the rate parameter is somewhere, and it's a continuous value, obviously, right? But larger than 0, larger than or equal to 0, it's somewhere between 0 and 8. It's not going to be my prior belief represented here in this prior distribution expresses the assumption that the lambda parameter cannot be, for example, 50, right? It's very, very unlikely that it would be 50, right? So that's the use of plotting the prior distribution graphically to eyeball the distribution to understand what it roughly represents for you as a prior. Okay, so coming back to our main goal, we have to decide on this prior. That's our current problem. We have a Poisson likelihood. Poisson likelihood takes the lambda parameter, and we're going to now figure out the hyperparameters a and b of the gamma distribution, right? So how do we do that? Well, we know the mean and variance, okay, of the two parameters. So not of the two parameters. We know the mean and variance of the lambda parameter. So what we are going to do is we are going to use the fact that the mean of a gamma distribution is defined as a over b. A and b are the hyperparameters that I'm trying to figure out right now, these two, right? So a over b is the mean of a gamma distribution, and a over b squared is the variance of a gamma distribution. That's an analytical result that one can work out. If you look at some textbook on statistics, on distributions or something, you'll see the analysis, the analytical result there. So what we can now do is that we know the mean and we know the variance. We know that the mean is 3 and the variance is 1.5. We know what the equation for the mean is, and we know the equation for the variance. So we have two equations and two unknowns, right? A and b. So let me just quickly do that. So I have, let's see if I can just make some space here. Yeah, this would be a reasonable place to write this, right? So actually I've done it here, but I'll just do it by hand here, right? So I'm going to redo everything here. So suppose I have a over b is equal to 3, a over b squared is equal to 1.5. So how do I proceed now? What I could do is I could rewrite a in terms of b here, a could be written in terms of b. So a would be equal to, you can't see this, can you? Let me write it here. A would be equal to 3 times b. Okay. So now once I know what a is in terms of b, I could, in this equation, I could replace a with 3b, right? So I'm going to do that now. So let me do that. So I have 3b divided by, what is it, b squared is equal to 1.5. Okay, so once I have this now, because I have b here and b squared here, this guy cancels out, so I get 3 over b is equal to 1.5. And what that gives me is that b, I've solved for b is 3 over 1.5. Okay, and so similarly, now that I know b, once I know b, I just plug 3 over 1.5 here and I get a. So I've solved for a and b. That's it, right? It's as easy as that. I just computed the hyperparameters a and b, so that's what you will get in the end once you do all the calculations, unless I made a mistake in my equations. You're going to get the result that a is equal to 6 and b is equal to 2, right? So I just solved for a and b given the mean and variance. Those are my hyperparameters that reflect my prior beliefs. based on what? Based on prior data in this case, right? So I had some prior knowledge. Okay, so these are my hyperparameters, A and B. A is equal to 6, B equal to 2. I can visualize that just like I showed you earlier. This now reflects my prior belief about the distribution of the lambda parameter. So I'm going to now use this prior distribution in the calculations that I'm going to do to compute the posterior up to proportionality, right? But one thing I want to show you here is that if you have some doubts about, whether you did this calculation correctly, you can always cross-check that using simulation, right? So let's generate some random data from a gamma distribution with A and B 6 and 2, right, respectively. So that's what I'm doing here. I'm just generating 10,000 data points from this gamma distribution. Then I compute the mean and the variance, and lo and behold, my mean and variance are exactly what we had defined earlier. So this gives me more confidence that I know how to multiply and divide numbers correctly. Okay? So that's a mistake that I often make doing simple calculations. You can mess up some numbers. So it's always good to cross-check. Always cross-check if you can. Sometimes simulation can help you get to cross-validate your apparently simple calculations which you might have gotten wrong. Okay, so now we get to the crux of the matter, right? So all this preamble is now bringing us to the point where we are going to multiply the likelihood with the prior. Let's assume that our data consists of a vector of values. So this is a vector, this is in boldface, by the way. And so I'm representing this vector with angle brackets. And each of these data points, these n data points, is assumed to be independent here, okay? So I'm assuming that these data, which are discrete numbers like 0, 1, 2, etc., they're coming from Poisson. And so what that means is that I'm assuming that this vector, boldface x, is coming from this probability density function, which is described here. So what you're seeing on the right-hand side is a product of n terms. What's going on here is that because this vector x, boldface x, contains n elements in the vector, what I'm doing is I'm taking each of these n elements, x sub 1, x sub 2, etc., and for each of those numbers in the vector boldface x, I'm writing out the probability density function in terms of the Poisson. So just focus your mind on the data point x1. Here I've defined the Poisson distribution for x1. You see that over here? And in the denominator, this normalizing constant is x1 factorial, right? So that's the probability density for the data point x1 given some lambda parameter value, right? Similarly, I would do that for x2, x3, all the way up to xn. So that's why I've got a product here. The reason I'm multiplying these is because I'm assuming that the n data points are independent. So I'm computing the joint density of these data. In other words, I'm computing the joint likelihood, treating lambda as the variable and the x's as constants, as discussed in chapter 1. The only variable in this equation is the lambda, and therefore I'm computing the joint likelihood of these n of lambda given these n data points. And so this expression here is very cumbersome to write because I have to keep writing those multiplication signs and all that. So a more compact way to do that is to use this product notation, which says that we just go from I equal to 1 all the way up to I equal to n, and we are just going to keep multiplying this term for different values of I. That's all I've done here. I've just written it in a more compact form here. Okay? Now, if you carry out this computation, right? So notice what's happening here. I've got lambda to the power of x1, lambda to the power of x2, lambda to the power of x3 for all the data points, all the way up to lambda to the power of xn. So what that means is that I've got lambdas multiplied with each other, and each of those lambdas has the exponent x1, x2, x3, x4, x5, all the way up to xn. So that means because I have these exponents here, I'm going to sum up those exponents, right? And so that's why I end up with lambda to the power of sum of all the x's. Similarly, the exponential part here, exponent minus lambda, is repeated n times. Okay, that's how I end up with exponent minus n times lambda. So if I unpack this product here, I can rewrite this product in the numerator in terms of exponent minus n times lambda, and then lambda to the power of the sum of x. In the denominator, what you're seeing is the normalizing constant for each of the n data points being multiplied, right? So you've got x1 factorial multiplied with x2 factorial, etc. So that's the denominator there. So all I've done is this equation is simply writing out the joint likelihood of the n data points. That's all. So let's go on and now add, go to the next step and multiply the likelihood. This is my likelihood which I just computed for the n data points. Multiply it with the prior, the gamma prior on the lambda parameter. Okay. So remember the gamma distribution, we just discussed it a few minutes ago. So this is the gamma distribution for the lambda parameter. Here are the hyperparameters A and B, right? They turn up here. And notice again that in the gamma distribution, all the terms involving lambda are constitute the kernel of the distribution, and all the terms not involving lambda, that means b to the power of a and this denominator gamma a, these represent together, they represent the normalizing constant. Okay. All right, so let's do this multiplication. So this is what I was talking about at the start of the lecture. When you look at this equation, it looks intractable. I mean, one doesn't really know what to do with it. It seems really complicated, but actually what's going on here is that there is one term here, the exponential, this exponential term here, and there's another exponential term here. So these terms are being multiplied together. Similarly, there is a lambda term here, right? And a lambda term here, and these are being multiplied together, right? So this should remind you of the beta binomial case. In the beta binomial case, we had the thetas and the 1 minus theta, and we were just multiplying those guys out and getting the posterior. Same thing's happening here. Okay, so let's just see how this goes. So one thing to notice in this equation now is that all the normalizing constants, we can just drop them, right? So the b to the power of a does not involve lambda, therefore it's part of the normalizing constant. Gamma a is also part of the normalizing constant. So these two guys we can drop, and also this denominator here is a normalizing constant, so we can drop all this. So that means we can figure out the posterior up to proportionality, right? Up to proportionality by simply dropping the normalizing constants, because they just complicate our lives. They don't really, we don't really need to think about them for the moment. Okay, so how do we do that? So let's look at the equation now with the normalizing constants dropped. Here's the exponent in the likelihood function for the Poisson, and this is the second term in the likelihood function, and here this part here is the gamma distribution kernel, the kernel of the gamma distribution. So let's just collect together all the common terms. Okay, so the lambda term is lambda to the power of sum of x, and there's another lambda here to the power of a minus 1. So I'm going to just sum up the exponents here. So I get lambda a minus 1 plus sum of x. That's all, right? Similarly, for the exponents, I have minus n lambda here in the likelihood, and in the gamma distribution, I have exponent minus b lambda, right? So if I put together those two terms, I could just rewrite them as exponent minus lambda and in brackets b plus n. The reason I did that is because what I want to do here is I want to write out the equation in a way that is expressing the gamma kernel, the kernel of the gamma distribution. Remember that the kernel of the gamma distribution involves a lambda term with some exponent -1. Remember, there's a -1 up there, and then the exponential term here, the exponent term here contains, if you go back to the gamma distribution, you'll see it's minus lambda b, right? Let's go back to the gamma distribution. Right, so for any variable x, right, the gamma distribution assumes that that one of the terms there is minus b times x. That x there is the random variable that we are modeling, right? So in our particular case, that x is lambda, right? So the gamma distribution is a distribution on lambda. That's why I'm not using x anymore. I'm using the term lambda here. So my gamma distribution is expressed in terms of the variable lambda, right? And that's why I want to express the gamma in terms of minus some b times lambda now. That's what's happening down here in this equation. Where is it? Here, right? So what I've got here now is the kernel of the posterior distribution expressed as a gamma distribution, right? So this is the kernel of a gamma distribution with updated a and b parameters. Remember when we defined the prior for the lambda parameter, the hyperparameters were a and b. Now the hyperparameters have changed, right? So in the posterior distribution, the parameters are now a plus sum of x and b plus n, where n is the number of data points. Okay, so here's what I've written down here. In the posterior distribution, I again have a gamma distribution with a new parameter which I'm calling a star equal to a plus sum of x, and a new parameter b star which is b plus n. So I just derived that in this calculation here by doing all these simplifications, right, up to proportionality. I ended up with, when I did all these calculations up to proportionality, I came up with the kernel of the gamma distribution, so I know what the updated a and b parameters are. So it's literally like the beta binomial case, except that it involves different terms, right? So and the parameter here is not theta but lambda, right? So that's the only difference here. But the underlying machinery is exactly the same as in the beta binomial case. Okay, so again, once I know the kernel of the distribution, so that a star and b star are known, I can figure out the normalizing constant, just like before, right? So I just have to take 1 over the integral of the kernel of the distribution with respect to lambda, and I will get the normalizing constant. So that would be the full PDF of the posterior distribution, which we can figure out once we have the posterior up to proportionality. Okay, so what's really interesting to notice here is that we started with a Poisson likelihood. We assumed a gamma prior on the lambda parameter, and the form of the posterior on the lambda parameter was also a gamma with updated a and b parameters, what I'm calling a star and b star. Okay, so that's the procedure that we have used now. We have used Bayes' rule to figure out the posterior. So let's work on a concrete example now, given some hypothetical data. I'm just making up some data here. So we're going to now look at an example to see how this machinery actually can be used in a practical setting. So suppose we have independent data points, regressive eye movements, right? So these are discrete numbers, for example, 2, 4, 3, 6, 1. I just made this up, okay? There's not anything representing reality. And let's say we have chosen as our prior the gamma 6, 2. So those are our hyperparameters on the lambda parameter. And let's say that given these data, if I sum these data points up, the sum of x is going to be 16, and the sample size is going to be 5 because I have 1, 2, 3, 4, 5 data points. So the sum of x is 16, n is 5. So given the analytical result I just computed, I can already tell you what the posterior of the lambda parameter will be. It will be gamma a star b star, where a star is a plus sum of x. So that means 6 plus 16, and b star is b plus n. So that is 2 plus 5, right? So we end up with a posterior on the lambda parameter that has the form gamma 22.7. So the a and b parameters that are updated based on the data that we have seen is 22.7, right? So given these two parameters, these are the parameters of the posterior distribution of lambda, we can now summarize that posterior distribution graphically. For example, in a paper, if you were writing out this result, you could summarize the mean, right, by looking at the a and b parameters. A over b is the mean, so that's 3.14, and the variance is a over b squared, which is 0.45. Right, so you could give some summary statistics on the posterior distribution of the lambda parameter, and you could of course graphically summarize it as well. That's what one would actually do when reporting this result in a paper, for example. So what we've done here is that we've carried out a conjugate analysis, right, of we first saw the beta binomial case, and now we've seen the Poisson gamma case. So these are two canonical examples of conjugate analysis where the prior on the parameter, the posterior on the parameter has the same form as the prior on the parameter given some particular likelihood. So the beta binomial case and the Poisson gamma case will give you a posterior where the posterior has the same form as the prior on the respective parameter. There are other such conjugate cases too, and when I talk about Bayes factors, I will bring up one more. That will be in chapter 13. Okay, so let's look at this section now, where I'm going to show you how the posterior mean is related to the prior mean and the maximum likelihood estimate. So let's start with the expression that represents the posterior mean. Remember that in the gamma distribution, suppose you have a gamma distribution with parameters a star and b star, the posterior mean is a over b. That's just an analytical result. So in our particular case, we just derived the posterior for the lambda parameter, and that's a star and b star, right? These are the hyperparameters for the posterior, and so the mean of the posterior is going to be a star over b star, which I can rewrite as in the right hand side, a plus sum of x in the numerator and n over n plus b in the denominator. Now I could rewrite this expression in the following way. So if you look here, what I've changed is, instead of writing sum of x, I'm writing n x bar. The way this emerged is as follows, right? So remember that the definition for the sample mean is sum of x over n, okay? So by the way, I'm just eliding the subscript x sub I here. I could have written x sub I here, and then I could have written n equal to I equal to 1 going all the way to I equal to n. Okay, so I could write something like to 1 to n x sub I. This would be the correct way to write this term here, right? But I'm just being lazy. I don't want to write all these subscripts and superscripts. So I'm just, whenever I write sum of x, x sub I, it means summing over all the n's, right? So I could just rewrite this equation as n times x bar and sum of x, right? That's all, right? So that's a standard trick in statistics. You can basically write sum of x as n times x bar. So that's what I've done here, right? Okay, so now I've rewritten this equation by rewriting sum of x as n x bar. If I divide both the numerator and the denominator by b, I get a very interesting transformation for in this equation. So what happens is I've got the numerator a plus n x bar, the whole thing divided by b, and the denominator n plus b divided by b. So if I unpack this bracket, if I open this bracket out, I get a over b plus n times x bar over b in the numerator, and in the denominator I get 1 over 1 plus n over b, right? This is just opening up the brackets in this after dividing by b. So what's interesting to observe here is that a over b is actually the mean of the prior distribution. So I can rewrite that as a variable, let's call it m. M represents the mean of the prior. So what I've got in this equation now, I've just rewritten this equation now in terms of a over b. So being rewritten as m, a over b is rewritten as m. So what this equation now says is that the posterior mean, remember this whole thing represents the posterior mean, right? So the posterior mean is actually a weighted sum of the prior mean and the maximum likelihood estimate. And we'll see this more easily if we separate out the numerators as separate fractions. So that's what I've done here. I take this entire expression and break it up so that I have m in the numerator here and x bar in the numerator here. And once I do that, what you'll notice is that we are looking at a weighted sum here. And the weights in this equation are the following. There's one weight, call it W1, which is equal to 1, and the other weight is n over b. So this equation I could rewrite in terms of W1 and W2, and now you see clearly that we are looking at a weighted sum. The posterior mean is a weighted sum of the prior mean and the maximum likelihood estimate. So the practical significance of this is very important. The practical significance is that if n goes to infinity now, okay, as sample size increases, what will happen is that this term will start getting more and more weight. So the posterior mean will start depending almost exclusively or exclusively on the sample mean, right? Similarly, if n is very small, then the posterior mean will largely depend on this term here, on the prior mean, right? So the interplay of the posterior mean with respect to the sample size is clear from this weighted mean equation here, right? Another interesting thing to notice is that the variance of the posterior is a star over b star squared. So if I rewrite the a star and b stars in terms of their expansions, that means a star is a plus n x bar and b star is n plus b. What you'll notice is that as n goes to infinity, the variance of the posterior will get smaller and smaller and smaller and smaller. So that is a very important insight, right? Because what that tells us is that as our sample size increases, we are going to get more and more precise estimates of the parameter of interest, in this case lambda, right? That will become very important for us later on when we are fitting complex hierarchical models where we have lots of parameters. Our goal for our scientific problem that we are studying will be to obtain a tight enough estimate of the parameter of interest in order to be able to draw meaningful inferences from the data. So that is something I will discuss in detail later on. So stepping back, we saw two examples of conjugate cases. One is the beta binomial, the other is the Poisson gamma. And we use simple algebra to derive the posterior up to proportionality. And I showed you the importance of the prior and the likelihood in determining the posterior. And I also showed you that the posterior is kind of a compromise between the prior and the likelihood. When the data are sparse, what will happen is that the prior will tend to dominate in determining the posterior, provided that the prior has some information in it, right? So I'm assuming some information in the prior that will dominate in determining the posterior if the data are very sparse. If there's a lot of data, then the prior will have less and less impact in determining the posterior. The posterior will be largely determined by the data that are available. So this is the interplay between the prior and the amount of data that you have in determining the posterior, and we will get a handle on this with practical examples later on in the coming chapters. One important case I want you to think about already is the situation where you have very sparse data. It can happen that you can only collect data from a few participants because it's a special population, for example, or you're working on a special language with very few speakers. In that kind of situation, the Bayesian approach can be very useful if you have useful prior information from previous studies. For example, somebody may have done a meta-analysis on a particular problem that you can use as your prior for the parameter in a future study with sparse data, or you may have expert opinions or prior beliefs about a particular problem that you're working on. You could express that quantitatively as an informative prior in your modeling, and that would then impact your posterior. So you could learn something even from sparse data if you have useful knowledge from previous work. So that is an application of Bayesian analysis that I will demonstrate in the later lectures that will come. You will see the importance of using information from previous studies in determining the posterior given some data that you have, some new data that you have acquired. In this way, you can actually build on your knowledge about a problem over the years. So most people that I know, they tend to work on a very similar class of problems over many years. It's not that today you're working on garden pathing and tomorrow you're working on local coherence and on another day you're working on similarity-based interference. You're just going from one topic to the other, flitting from one thing to the other without any connection between them. Usually there's a thread that you're trying to pull apart. You're trying to get at a particular, understand a particular phenomenon. And so what's happening is that you're accumulating knowledge over the years through your own experiments and through other people's published studies. And you can use that information in the Bayesian analysis through the priors to build on what you know and incrementally gain knowledge about the problem that you are trying to study. So until now, I've been showing you some toy examples involving the beta binomial and the Poisson gamma. Those are not, these are not, approaches that we can use in real life data analysis because we usually have repeated measures data, dependent data, and we need much more complex models. And in those situations, we cannot do this kind of analytical analysis unless we grossly simplify the problem, of course. So in those situations, in more realistic settings, we're going to use computational methods. So we're going to use probabilistic programming languages like STAN and BRMS, which is a front end for STAN. We are going to use sampling algorithms to derive samples. Computationally, we are going to derive samples of the posterior distributions. So what we did here in the examples that I showed you in this chapter is that we were able to actually describe the posterior distribution as a gamma distribution or as a beta distribution, right? But now what we will do is we will get samples of the posterior distributions of the parameters of interest, but we won't have any closed form solution like a gamma posterior or a beta posterior for the parameters of interest. And for that, we will need computational tools, and that's what we will discuss in the next chapters. I do have a lecture online on sampling algorithms. I will not discuss them in this course because there's just not enough time, but you can take a look at this lecture and get a feel for what it means to do sampling from a particular distribution. But I just want to remind you that we have already looked at examples of samples from a distribution. So the R family of functions, for example, the R norm function, that function is generating samples from a particular distribution. The R Poisson function is generating samples from a particular distribution, right? And the R gamma function would also do that, right? So these are three examples that we have seen, and R binom also we have seen, right? R binom. So these functions generate samples from a particular distribution, and these algorithms will do the same thing in the sense that they will give us actual samples from the posterior distribution given some likelihood specification and given some priors on